Good afternoon. Just looking at what we have in working with operations existing between functions, and we looked at a few general cases as well as looking for the domain among the operations. And now, let's say if we were looking at specific input instead of just the variable x, okay, and we'll just call this part operational functions involving specified inputs. Okay. So we'll still be working with the functions f and g at the moment. Okay. And let's say if we have, let's see, not just two, but we'll say we have three given functions. And we'll say that we have f of x is going to be 2x plus 3. And we'll say that we have g of x is going to be x minus 3. And we'll say we have h of x. Will be equal to x plus 10. Okay, so given what we have here and looking at specified inputs, and we'll say we will determine, let's see what we have for f plus g of 4. And we'll say we have f minus h of 7. And we'll say we have in the mix, we'll say we'll have the determination of g times h of 5. And we'll say that we have in the case of a quotient function value, we'll see what we get for h over f of negative 2. Okay, so we have three linear functions assigned, okay, for f, g, and h of x. Okay, now for what we have for f plus g of 4, and the way you can look at this, okay, so just like f plus g of x, okay, can be split up as the sum of f of x and g of x. We can say that f plus g of 4 is equal to f of 4 plus g of 4. And what we can do now is identify the values of f of 4 and g of 4. Okay, so we have for f, okay, now we've got f of x is equal to 2 times the input plus 3. Now for f of 4, okay, so we're going to be using the f function. Okay, f of the input is equal to 2 times the input plus 3. And we have the input at 4. Okay, so we have 2 times 4 is 8, plus 3, which is going to be 11. And for what we have in the case of working with g of 4, okay, so for g of 4, okay, g of the input is equal to the input minus 3, so we have g of 4 is equal to 4 minus 3, so that is equal to 1. So for f plus g of 4, okay, so we're looking at 11 plus 1. And so we have for the output itself, okay, this will come out to 12. Now for what we have in the case of f minus h of 7, okay, and just as we can break up the sum function as a sum of functions, we can break up the difference of functions, the difference function as a difference of functions. Okay, so here in this case, we can say that we have for f minus h of 7, we can say we have f of 7 minus h of 7. Okay, so we have for f of 7, again we have 2 times the input plus 3, so we have the input at 7. You have 2 times 7 is 14 plus 3, and so we have f of 7 is equal to 17. Okay, now with our function h, where we have x set equal to 7, okay, so h of 7, again, h of the input is equal to the input plus 10. So I have h of 7 comes out to 7 plus 10, which is also at 17. Okay, so we have for f of 7 minus h of 7. Okay, so f of 7 is at 17. We've got subtraction. Again, h of 7 we have at 17. And we have for the follow through, okay, we have 17 minus 17 is equal to 0. Now for g times h of 5, okay, and for the product function, I can split this up as the product between the functions we have in g and h. So in this case, we're looking at g of 5 times h of 5. Okay. And so for what we have in the case of g of 5, referencing g of x, so g of 5 is equal to 5 minus 3. Okay, so this will come out to 2. For h of 5, again, h of the input is equal to the input plus 10. So we have 5 plus 10, so this will come out to 15. And so with the values determined, okay, so we're going to have 2 times 15. And so for g times h of 5, okay, we'll have the product to end up at 30. All right, and we have, in the case of the quotient function, okay, so we have for h over f of negative 2, again, for the quotient function, we can split this up as the quotient of the functions where we have h of negative 2 in the numerator and f of negative 2 in the denominator. Okay, so we have for h of negative 2, okay, so h of negative 2, okay, so this would be negative 2 plus 10, which is 8. And for what we have in the case of f of negative 2, okay, so we're looking at 2 times negative 2 plus 3, and we have 2 times negative 2 is negative 4 plus 3. Okay, so we have negative 1. Okay, and so going back to the quotient function, okay, so we have, again, so we have h of negative 2 is 8, and we have f of negative 2 is minus 1. And here we have 8 divided by negative 1, and a positive over a negative is a negative, and for this outcome, we have minus 8. Okay, from section 1.8, okay, and we have for this set of functions, f of x, g of x, and h of x, okay, says to evaluate. And for what we have in the case of number 10, in case you have g minus h of 2, and just setting things up here. So you can write this as the difference between g of 2 and h of 2. Alright, so for what we have in the case of g of 2, okay, so g of 2, we're looking at the absolute value of 2 plus 4. 2 plus 4 is 6, and the absolute value of 6 is at 6. And for what we have in the case of h of 2, okay, so referencing h of x, okay, so with x at 2, so you have 1 over 2 minus 3, and 2 minus 3 is negative 1, and 1 over negative 1 is minus 1. Okay, so we have, looking at what we have in the follow-through. Okay, so we got g of 2, again, is at 6, and we have subtracting h of 2. So we're looking at the subtraction of negative 1. Again, subtracting a negative is the same as adding the additive inverse. Okay, so you have 6 plus 1. So for g of 2 minus h of 2, okay, we have for this outcome, we're going to have a positive 7. All right. Now for what we have in the case of the next item, okay, and we have for number 12, okay, so we're looking at h times g of 4. Okay, so we have a product function we can rewrite as determining the product of h of 4 times g of 4. Okay, and looking at now h of 4, okay, so you have for h of 4, okay, so we're referencing again h of x, so you have 1 over 4 minus 3. Four minus 3 is 1, and so h of 4 is equal to 1, and in the case of g of 4, okay, so we're looking at the absolute value of 4 plus 4, and so we have the absolute value of 8, and that is going to be at 8. Okay, so supplying the values, okay, so you have h of 4 times g of 4, again, h of 4, okay, we have at 1, we have times g of 4, which we have at 8, and for this end result, okay, we have at 8. Okay, now, for what we have in the case of number 14, okay, so you have f plus h of 5. So we say we have f of 5 plus h of 5. Okay, so we have in the case of f of 5, again, referencing negative 2x So we have negative 2 times 5, okay, which is negative 10. And for what we have in the case of h of 5, okay, so you have h of 5 is going to be equal to 1 over 5 minus 3. And so this will come out to 1/2. And so looking at what we have now, okay, so we've got f of 5 we have at negative 10. And we have plus h of 5, which again we're going to have at 1/2. Okay, and it looks like we're going to have a non-integer value for this outcome. So for negative 10 plus 1/2, okay, we can say we have like negative 10 will be negative 20 halves. Plus 1/2, and so we have for the results in this case we have negative 19 halves, or you can also write that as a mixed number or decimal with negative 9.5. Okay, now for what we have in the case of numbers 16 and 18, okay, and we have with these items, okay, we're looking at the values of quotient functions. Okay, and for what we have in the case of h over f of 7, okay, so you have h of 7 all over f of 7. Okay, and looking at specifying the values, okay, so we have for h of 7, okay, so you have 1 over 7 minus 3. And so we have it 1/4. And in the case of f of 7, okay, so you have negative 2 times 7. Which we have at negative 14. Okay, so filling in the values. Okay, so again we have h of 7, okay, which we have at 1/4. And we have all over f of 7, which we have at, again, at minus 14. Okay, so we have in the case of the setup, okay, so you have 1/4 divided by negative 14. And what I can do here is that if I'm dividing by a number, I can put this in terms of multiplication, where if I divide by a number, it'll be the same as multiplying by that number's reciprocal. So in this case, I can say you have 1/4 times, and the reciprocal of negative 14 is going to be negative 1/14. And here we have a positive times a negative is a negative. And 1/4 times 1/14, okay, that's going to be 1 over 56. So the end result here is going to be minus 1/56. Okay, now for what we have in the case of h and g, okay, so you have h over g of negative 4. Okay, and for h of negative 4 over g of negative 4, okay, so you have h of negative 4 so you have 1 over negative 4 minus 3, so this would be 1 over negative 7. And so in the case of h of negative 4, okay, this is going to be a minus 1/7. And in the case of g of 4, okay, correction, g of negative 4. Okay, so we're looking at absolute value of negative 4 plus 4. And here we have the absolute value of 0. And this will only be 0. And so just inputting the values, okay, for h of negative 4 as well as g of negative 4. Okay, so we have for h of negative 4, so we have negative 1/7, and we have for g of negative 4, okay, we have at 0, and guess what? Okay, we have a 0 denominator. And so we have for this end result, okay, number 18 ends up becoming undefined. And we have, again, we have with our general functions, with the sum difference products, as well as the quotient functions. Okay, again, in terms of the domain, again, we have the sum difference and product functions. Those are going to have the same domain, and they'll be formed, okay, by combining the restrictions where they exist between f of x and g of x. And again, with the quotient function, okay, again, this could be the function, okay, that can have a distinct domain because you already have a pre-existing situation where the denominator, in this case g of x, cannot be 0 in value. And let's say that just kind of going back to kind of melding together operations between functions as well as determining the domain. And let's say if we have so again, we have f plus g of x, f minus g of x. Again, we have the quotient function. And also determining their domain. And we'll say that we have given, and we'll say that we have, okay, I think we started out with linear functions the other day, but I'm going to have quadratic functions in this case. And we'll say that we have f of x is equal to x squared plus 1 and we'll say that we have g of x is equal to x squared minus 4. Okay, so for what we have in the setup, Again, we'll reference these two functions again. All right. Let's go ahead and copy this. Okay, so for what we have in the case of f plus g of x, we have f of x plus g of x. Again, so we have with f of x, okay, so you have x squared plus 1. And for g of x, okay, so we have x squared minus 4. Okay, so you don't have any negative signs, okay, in front of either of these functions. And once we take out the parentheses, okay, you're going to have the same terms again. So we have, in following through, okay, so we got x squared plus 1 plus x squared minus 4, and combining like terms together. So we have x squared plus x squared so this will come out to 2x squared minus 3. Okay. Now for the difference function, okay, with f of x minus g of x. Again, so we have at the front, we have f of x, whereupon we have the quantity of x squared plus 1. We have minus, again, all of x squared minus 4. And removing the parentheses, okay, so you have f of x, again, we have with x squared plus 1. And with g of x, which is being subtracted, so x squared minus 4 will be changed over to negative x squared plus 4. And combining like terms, notice you have x squared and negative x squared, so we have additive inverses. These will cancel out, and we have 1 plus 4, which is going to be at 5. Okay, so the result here is going to be a constant. And in the case of the product function, okay, so we have with f of x times g of x. Okay, again, so we have f of x at x squared plus 1, and g of x we have with x squared minus 4. And looking at distributing, okay, so if I FOIL out, okay, we have first part, we have x squared times x squared, which would be x to the 4th. Outside product, we have x squared times negative 4, so we have negative 4x squared. Inside product, we have 1 times x squared. And the last product, okay, we have at negative 4. Upon combining the like two terms in the middle, okay, we have for the product output, we have x to the 4th minus 3x squared minus 4. And for what we have in the case of the quotient function, okay, so you have f of x over g of x. So f of x, okay, we have an x squared plus 1 for g of x, okay, we have x squared minus 4. Okay, and you can leave it in this form. There's no common factor. The greatest common factor between the numerator and denominator, okay, we have at 1. And if I were to write this out in any other fashion, you could take the difference of squares and factor to x plus as well as x minus 2. Okay, so this is what we have for the outputs, okay, for the sum, difference, product, and quotient functions. Now, where we have domain to come to the scene, again, we have the sum, difference, and product functions to have the exact same domain. Let's see if I can relay this here. Okay, so first things first. Okay, so we got, again, for the sum, difference, and product functions. Again, we had the same domain. Okay, now, looking at it, okay, essentially through the prism, okay, of any restrictions that are applied for the individual functions involved. Okay, so we have with f of x and g of x. Okay, so f of x we have x squared plus 1, and g of x we have at x squared minus 4. And for what we have with f of x and g of x, okay, notice we don't have an even root radical, nor do we have a fraction that can lead up to a zero denominator. So both f of x and g of x, okay, are direct functions, okay, and we can plug in anything for x, whether we have a 0, a negative value, or a positive amount, okay, for the input. Okay, so we have our f of x itself. Okay, we have no restrictions. And since f of x has no restrictions, okay, we have for the domain of f of x, okay, that is going to be the set of all real numbers. Again, we can plug in any negative, 0, or positive value for x, and so it'll come out to a defined expression for f of x. And the same thing applies for g of x. Again, you have like you can plug in anything for x from the real number system and come out to a defined output. So like f of x, g of x also has no restrictions, and the domain is also going to be the set of all real numbers. All right. And for the sum, difference, and product functions, again, they're going to have the same domain, and the domain is going to be defined by combining the restrictions, if any, that exist between the immediate functions involved. In this case, where the immediate functions are f of x and g of x, and between them there are no restrictions. And guess what? That's going to carry over for the sum, difference, and product functions. Okay, so for the sum function, no restrictions. Domain is going to be the set of all real numbers, and this will cascade over to the difference as well as the product functions. Okay, now in the case of f over g of x, again, because g of x cannot be 0, okay, we have possibility, okay, that f over g of x can have a domain that is different. And for what we have in this particular regard, so again, just going back to f over g of x, Okay, so you have f of x over g of x. So you have this bit of history to repeat. Okay, and since you got a fraction, unlike any of the cases with f of x alone, g of x, as well as the sum difference in product functions, we now have the layout for the quotient function to have a restriction. And the restriction is that, once again, the denominator cannot be zeroed. Okay, so here we have the x squared minus 4 cannot be zeroed. And anything that forms x squared minus 4 cannot be 0 in value either. Okay, so, and for the difference of squares, okay, the factors cannot be 0. Okay, so for x plus 2, okay, x plus 2 cannot be 0. So x cannot be negative 2. Also for x minus 2, since this cannot be 0, we have the x cannot be equal to negative 2. So we're not going to have the domain to consist of all real numbers. Again, just going back to the setup for interval notation. Again, graphing is a viable lead-in to just specifying what terms will be in the domain. Okay, so again, x is going to be exclusive of negative 2 as well as positive 2. But it is going to have everything else around these numbers, between, and also where we have less than negative 2 and greater than negative, or I should say greater than positive 2. And so for what we will have in the case of f over g of x, again, you had the restrictions that x cannot be negative 2, and that x cannot be positive 2. And so we're going to have for the domain, okay, we have two exclusions, okay, and so we're going to have an interval notation, so we have 3 sections, okay, and at the lowest end, you're going to have those values of x less than negative 2, and bypassing negative 2, and we have next in line, we have those values between, but not including, negative and positive 2, and we have for the rest of the makeup of the domain of the quotient function, again, we have those values of x greater than 2, and that portion will be symbolized by parentheses around 2 and infinity. And again, not always, but in a lot of cases, in terms of the domain, for what we have among the sum difference products and quotient functions, okay, the quotient function can have a domain that is different from the other operations, and that one happens to be such a case. All right, now just looking at the items now, and one might be wondering, okay, what does that exactly mean whenever you're talking about combining restrictions? I'll give you kind of a case here and sort of bypass having to operate in terms of the sum difference, product, and quotient functions. And let me give you, say if you're looking at just determining the domain. So I've determined the domain of f of x, g of x, and we'll say we have given, and we'll say that we have f of x is equal to, let's say we have 3 over x plus 4. And we'll say that we have g of x is equal to x minus 4 all over x plus 1. Okay, so we have just kind of creating a backdrop here. Okay, so we have in terms of the procedure. Okay, so if we look at f of x, okay, so for f of x equal to 3 over x plus 4, okay, again, we have a rational function, and again, a rational function does not allow a zero-valued denominator. Okay, and so we're going to have here, for f of x, okay, we have x plus 4 cannot be 0, and I'll just go ahead and specify what x cannot be. So in this case, x cannot be negative 4. If it were, f of x would have a zero-valued denominator. Okay, now, in the case of g of x, okay, so you have a couple of variable expressions involved. Okay, with x minus 4 and x plus 1. Okay, but again, the restriction is going to lie with the denominator portion. And you can have like a zero top part of the fraction as long as the bottom number does not happen to also be 0. So in this case, for f of x, again, x plus 4 cannot be 0. Now for g of x, x plus 1 cannot be 0. And if x plus 1 cannot be 0, we have that x cannot be negative 1. Okay, now for the operational functions, for f plus g, f minus g, f times g, and f divided by g of x. Okay, again, for these to be defined, we have to keep the functions immediately involved defined as well. So I have to keep f of x real as well as g of x. Okay, so to keep f of x real, again, none of the functions that follow can allow x to be negative 4. And since we're working with g of x, again, we cannot have x to be negative 1. Okay. So again, for the sum difference and product functions, again, their domain will be defined solely by the restrictions combined from the individual functions involved. Okay, whereas with the quotient function, there could still be more added to the story. Okay, now for f of x, okay, again, we can go ahead and specify that domain. So we have, with the exclusion of negative 4, okay, we have what will be involved here. We have those values of x less than negative 4, and those values of x which will be greater than negative 4. And for g of x, okay, so you have negative 1 excluded. So we have, for the domain, you're looking at, again, just splitting up into two portions. Those values of x less than negative 1 and those values greater than negative 1. Okay, so f of x and g of x, okay, we have split up into separate interval sections where we have less than and greater than the excluded values concerned. Now, for the sum difference and product functions, okay, again, we have not one but two exclusions. Again, the sum difference and product functions will have the same domain. Okay, and so if you were to rank order, now we have again, we have at the lowest extreme, so you're looking at set of values x less than the lower of the exclusions. In this case, we'll have negative 4. Okay, now we're going to bypass negative 4 and go beyond negative 4. And the next stop is going to be approaching negative 1. So those values of x less than negative 4, and then you have those values of x greater than negative 4 and less than negative 1. And like negative 4, negative 1 is going to be bypassed, and there's no other exclusion after applying negative 1. So for the rest of the set, we have those values of x greater than negative 1. Okay. And so we have sort of an inductive pattern. Okay, have like one exclusion, two subintervals, and for the sum difference and product functions, we have two exclusions but three subintervals. And when you have, like in these cases, like for the number restricted values, number subintervals forms will be even one higher. Okay. All right. Now, for the quotient function, again, to be able to work with both f of x and g of x. Again, x cannot be negative 4 to satisfy f of x. X cannot be negative 1 to satisfy g of x. But for the entire framework, there could be some other fine restriction details that could be further applied. Okay, so we have for f over g of x, All right, so we have f of x over g of x. And again, we have f of x, we have 3 over x plus 4. And g of x, we have x minus 4. All over x plus 1. And here we have ratio where we have a fraction over a fraction. And in this particular case, now, if you got a fraction where you have like a denominator fraction, what you can do is that if you're dividing by a fraction, you can rewrite this in terms of multiplication, where dividing by a fraction will be the same as multiplying by the fraction's reciprocal. Okay, so I got 3 over x plus 4. And again, just multiplying by the reciprocal. And so we have in the follow-through case, you're going to have 3 times the quantity of x plus 1 and we have all over x plus 4 times the quantity of x minus 4. Okay, so just looking at what we have for the restrictions. Again, when we started out, okay, we had to keep x plus 4 non-zero, and for g of x, had to keep x plus 1 non-zero. And if you notice, okay, we have 3 over x plus 4, and then once I take the reciprocal of the denominator fraction, guess what? We have yet another restriction. Because what was the numerator for g of x? That is now in the denominator position. So this time, okay, along with x not being negative 4 and x not being negative 1, with the preconditions laid out from f of x and g of x, we have with the follow-through, with the quotient function, we have also that x cannot be positive 4. And so this time we will have 3 specified restricted values. Okay, so you're going to have yet another interval subset. Okay, and so just rank ordering from smallest to largest. Okay, so you have negative 4 still the smallest of the exclusions. So we have those values of x less than negative 4, followed by those values of x greater than negative 4 and less than negative 1. And again, I'm going to bypass negative 1, and instead of going out to infinity, I have this roadblock with the exclusion of 4. So this time we have values of x greater than negative 1 and less than 4, and bypassing 4, and with 4 as the highest restricted value, we have for the rest of the domain, then we have those values of x, okay, which will be greater than 4. And say if we look into the next portion, okay, where we have from section 1.8, okay, see we have with the exercises from 20 to 26 even. Now we have in the layout, okay, it says for these 3 functions, okay, so you have r of x is equal to negative 3x, and we have p of x we have is equal to x squared plus 3x, and q of x, okay, we have is equal to the square root of 1 minus x. And now for what we have in this regard, okay, and just again just mentioning some things here, okay, for r of x is equal to negative 3x, okay. So we have for r of x is equal to negative 3x. Okay, we have a linear function, and you can plug in anything for x. So for r of x alone, we have no restrictions. And for what we have in the case of p of x, okay, so p of x we have equal to x squared plus 3x. And again, we have direct terms, no even root radical, no fraction. So like r of x, it can have x be 0, positive, or negative throughout. Now for what we have in the case of q of x, is equal to the square root of 1 minus x. So you have for the square root of 1 minus x. Again, we have the nature of the radical to be an even root, since you have a square root. So in this particular case, because they have a square root, 1 minus x cannot be negative. Okay, now, as long as q of x is in direct terms, okay, 1 minus x can be 0, and it can also be positive. So just for the general inequality setup, so with q of x as the square root of 1 minus x, okay, 1 minus x can be greater than or equal to 0, and specifying what will be allowed for x. Okay, so if I isolate the x term, okay, so we'll have that negative x is greater than or equal to negative 1. And again, if I change the signs, going from negative to positive x, again, if I multiply or divide by a negative, the inequality direction is going to change. Okay, so transition from negative to positive x, we'll have that x is less than or equal to 1. Okay, so while r of x and p of x do not have restrictions, we have q of x, on the other hand, is going to have a restriction that x is less than or equal to 1. All right, and in looking at what we have for the operations between the functions, now we have with p minus r of x, for p minus r of x, okay, so you're involving the functions p of x and r of x, so there are no restrictions. You can already go ahead and say that the domain is going to be the set of all real numbers. Okay, so with p of x minus r of x, so again we have p of x so x squared plus 3x, and we have minus r of x. So we are subtracting negative 3x. So for p minus r of x, again translating to p of x minus r of x, okay, we have for the output, okay, that is going to be at x squared plus 6x, okay. And again, with the nature of the function being a difference function, we're limited to combining the restrictions, if any, that exist between p of x and r of x. And note that we have no restrictions. And the domain is going to be the set of all real numbers. Okay, now for r times q of x, okay, for r times q of x, now you're going to have a restriction. While r has no restriction, q of x is going to have the restriction that x be less than or equal to 1. Okay, and just looking at what we have with r times q of x, and there's really not that much to do with this one. So you have r of x times q of x. R of x, we have negative 3x. And q of x we have with the square root of 1 minus x. And no distributing can be done in this case, right? So you're just filling in negative 3x for r of x and the square root of 1 minus x for q of x. Okay, this will be our results. And for what we have for r of x and q of x, again, combining the restrictions, and we have the only restriction comes from the q of x portion. Again, that is because of this particular part. And so with the only restriction that x is less than or equal to 1, okay, so we have in the case of the domain, again, you can construct a visual. Less than or equal to 1, so you would have like a solid point on 1, an array that's going to go continuously to the left. And heading out in the direction of negative infinity. Okay, so just putting this in interval notation. Again, you have the lower limit approaching negative infinity. Again, infinities are balanced, so we have an open parenthesis, and we have approaching and including the value of 1, which in this case is going to be in the bracket. Now, in the case of 24 and 26, okay, now those are interesting, okay, especially in looking for the domain. Now for q over r of x, again, you have a couple of quotient functions. And again, we have here for q of x over r of x. Now for q of x, again, we have the square root of 1 minus x. And for r of x, okay, we come out to negative 3x. And just like a lot of the quotient functions, okay, just substituting for the numerator and denominator oftentimes will lead to the simplest form, though not always. Okay, now for the domain, okay, so there are some needles to thread, okay. Now, first of all, okay, we had the functions involved. Now we have q of x and r of x. Now, in direct terms, now r of x has no restrictions. Now we got q of x, okay, so we have that x is less than or equal to 1. Okay, so we have, now for q of x, to keep it defined, okay, we have the restriction, okay, that x is less than or equal to 1. Now, for what we have in the case of r of x in the denominator, so again, you have r of x equal to negative 3x in the denominator. Now, if I had negative 3x in direct terms, like if it were in the numerator, there would be no restriction. But since I have negative 3x's in the denominator, it's going to follow that, okay, negative 3x cannot be 0. So this will dictate that x cannot be equal to 0 either. Okay. Okay, so for the quotient function, I'm looking at meeting both of these restrictions, okay, for q of x and also the fact that r of x is in the denominator. Okay. Now we have with our values of interest, with the exclusions and the restrictions involved. Okay, so you have 0, which is going to be excluded. You also have 1, which you have as the upper limit, okay, to which x can be regarding q of x. Okay, so looking at what we have in the mix. Okay, so for 1, okay, thanks to x is less than or equal to 1, and since q of x is in the numerator, okay, we can have x equal to 1. Okay, now we got 0 is a value that is less than 1. Okay, but now we got this other situation, kind of a juggling act, keeping q of x happy and as well as what is the overall ratio, just kind of avoiding a 0 denominator. Okay, so in this case, so 0 is not allowed. So for what we have here, so 0 is disallowed. Everything else that is less than or equal to 1 is going to be in the mix. Okay, so for what we have in terms of the activity, okay, so you're starting out, okay, have x is less than or equal to 1, but you have the blip with 0 excluded, but once we go past 0 and proceed to the left, we can continue on out to the left. Okay, so for this quotient function, we're going to have for the domain, satisfying what we have for q of x, as well as the fact that r of x is in the denominator. So we have at the lower end, okay, so we have going from negative infinity, approaching but not including 0. And again, we have bypassing 0 and proceeding past 0. So you have those values of x greater than 0, and for the rest of the section you have approaching and including 1. And this will be the interval notation for what we have regarding the domain of this particular rational function. Okay, and yeah, so there were some pretty, yeah, it's kind of a testy situation with the needles to thread, and this is kind of a similar situation. And if you notice, we have not q over r, but r over q of x. And for what we have in this one, okay, so for r over q of x, we have r of x over q of x. And so you're going to end up with the reciprocal of what we have for number 24. Okay, so you have negative 3x over the square root of 1 minus x. Okay. And for what we have now, r of x is in the numerator, so there's no restriction to apply to r of x, which was unlike with r of x when it was in the denominator. Okay, so you can have, in this case, you can have x to be 0 in the numerator. But now for what we have in the case of q of x, okay, we have further restriction, again, for the radical. Again, 1 minus x cannot be negative. And also because 1 minus x is in the denominator. Okay, we have the added twist now that 1 minus x cannot be 0. It could be when it was in the numerator, but with it in the denominator, we have this added twist. Okay, so 1 minus x cannot be negative, it cannot be 0, so that means that 1 minus x has to be positive. And so we have for the defining inequality, okay, so we had that 1 minus x is greater than 0. Again, isolating the x term and subtracting 1. So you have negative x is greater than negative 1, and a bit of history repeating. Just changing the sign value is going to change the direction of the inequality. And so in this case, we have the x is less than 1. Okay, and so we have for x is less than 1, and this is going to be the lone restriction. So 1 is not included, but the values less than will be in the domain. Okay, so for 26 case, we're going to have for the domain. So reading in order from left to right, in case you have going from negative infinity and approaching, but not including the value of 1. Okay, we're going to have what will be referred to as the composition of functions. And you can use different letters. So I'm just going to go with f of x and g of x for the general cases. Okay, so for functions, f of x and g of x. Okay, for the composition notation. Okay, so you have like a circle that separates the variables. It has nothing to do directly with the sum, difference, product, or quotient functions. But for that, we'll cite the letter O. Some might call this fog x. But this particular arrangement is going to be read f composed with g of x. And in terms of its equivalent expression. Okay. Now we've had stuff like when we first looked into functions, we had that x was like the input or independent variable, and y was the output or dependent variable. Well, in the case of f composed with g of x, so you have like an intertwining of two functions. And for f composed with g of x, if you were to cluster this together, you would have f of g of x. And for what you have here for g of x, again, that is going to be the input function. And for what we have in the case of f, the follow through with f, okay, that is going to be the output. And just using a little bit of switching around or inversion. If I had a different sequencing, now for one instructor call this goth x. But for what this means, okay, you have just like a role reversal in terms of what the input and output will be. And this part is going to be read g composed with f of x. And again, just intertwining what we have going on between the functions g and f, where we have g composed with f of x so you have g of f of x. Okay, so this time it is f of x, that is the input function. And the g part that is used to follow through, okay, that is going to be the output. Okay, and just looking at what we have as samples, okay, that we have regarding compositions of functions. And we can say that so if I'm to determine f composed with g of x, as well as g composed with f of x, and just a couple of cases here. We'll say we have f of x is equal to x plus 2, and we'll say we have g of x is equal to 3x minus 4. Okay, so for what we have right now, okay, so you have, looking at f composed with g of x, okay, so right now we got f of g of x. Okay. Again, so we have for the setup, I'm just going to kind of draw a parallel here. So with f of x equal to x plus 2. Okay, so operating along the lines of the output function f. Okay, so f of the input is equal to the input plus 2. Now we got g of x as the input, so f of the input is equal to the input, which is g of x, followed by the addition of 2, and then specifying just what the composition is going to be. So I got g of x plus 2. Well, what is g of x? Well, that expression is going to be 3x minus 4. So you got g of x plus 2. Again, we have 3x minus 4, followed by the addition of 2. And once you put together, okay, we have for the resulting expression, okay, this will end up at 3x minus 2. Now for the reverse order, okay, for I have g composed with f of x. Okay, so in the case of g of f of x, so the output function, okay, is going to be what we have for g. Okay, so again, just a backdrop here. G, the input, is equal to 3 times the input minus 4. Again, duplicate, okay, where the input is now f of x. So we have 3 times f of x minus 4. And f of x we have at x plus 2. And looking at the follow through. Okay, so we have 3 over the quantity of x plus 2. So this would be 3x plus 6. And taking away 4. And for the resulting composition, okay, so that is going to end up at 3x plus 2. Okay, and notice, okay, you're still working with conceptually the same functions to begin with, but the different sequencing in the composition can result in different expressions. Though there are those special functions that can have, the f composed with g and the g composed with f of x to be the same, and those will be what I refer to as one-to-one functions. Okay, but that's going to be a topic down the road. And let's say that if we have let's say we have f of x. This time we'll say that we have f of x is equal to let's say we have x plus 5, and we'll have g of x to be a quadratic function. We'll say we have g of x is equal to x squared minus 2. Okay, so for f composed with g of x, okay, so we're looking at f of g of x okay, then once you're setting that up, okay, this is the easy part, okay, and then you might ask, okay, what do I do next? Okay, so just keep in mind, okay, you're operating along the lines of the outside variable. Okay, so going with that reference, okay, so you have f of x, f the input is equal to the input plus 5. Guess what? For the input at g of x, then we have g of x plus 5. Okay, and then just taking care of the functional notation and replacing with the algebraic expression that defines it. So you have g of x, we have x squared minus 2, followed by the addition of 5. And so for what we will have here, okay, so you have x squared minus 2 plus 5, and this will come out to x squared plus 3. Then we have in the case of the role reversal, for g composed with f of x, okay, so you have g of f of x. Okay, again, so for this arrangement, okay, you're going to work along the lines of g. Again, for what we have for g, you have g of the input is equal to the square of the input minus 2. Okay. Okay, so this time we have the input at f of x. So now I'm going to be squaring out f of x. And then crossing over to the application threshold. Okay, so f of x, you have x plus 5. So squaring f of x is going to translate to squaring x plus 5. And again, just for the square of x plus 5. Again, so you have x plus 5 times itself. Again, so you have x squared plus the outside and the inside products plus 25 . Okay, so for the square of x plus 5, okay, so you have x squared plus 10x plus 25. And we have followed by the subtraction of 2. So for the result of g composed with f of x, okay, we'll end up at x squared plus 10x plus 23. Okay, and that's definitely going to be quite distinct from x squared plus 3.